Okay, so in yesterday's class, we have studied till second law of thermodynamics, and then we also appreciated that what are available energy and unavailable energy, right? So let us do few problems based on that, and then we will move ahead. Okay. Okay, so let us read this question first and then we'll answer. It says that which one of the following statements is correct. So let us read the statements one by one. It says that a machine which violates Clausius statement will violate first law of thermodynamics. So this is absolutely wrong. Why? Because Clausius statement, we have seen this statement related to second law of thermodynamics. Next statement, a machine which will violate Kelvin Planck will violate the first law. This is also wrong. Why? Because Kelvin Planck and Clausius are the statements of second law of thermodynamics. Okay. Then it says the third one, a machine which violates the second law of thermodynamics will violate the first law of thermodynamics. This is also wrong. Why? Because this is not always necessary that this will get violated. We have seen the example, right? So the last option is that a machine which violates Kelvin Planck's statement will violate the Clausius statement. So this is correct statement. See, the proof is very lengthy, but we should not be worried about that. But we should always keep in mind that a statement, let us say that there is a mechanism or any machine which is violating Clausius statement or violating Kelvin Planck, then it will violate Clausius statement also. Means vice versa is also true. Means if you are violating, if any one of the law, any one of the statement, one of these statement, Kelvin Planck or Kelvin Planck or Clausius is violated, then means if Kelvin Planck is violated, Clausius will always be violated. So what should I write? That if any one of the statement Kelvin Planck or Clausius is violated, other one is automatically, other one will also be violated. Okay, fine. Let us go to the next question. It says that which of the following devices complies with the Clausius statement? See, very important part of this question. It says that which of the following devices complies with the Clausius statement of second law. So see how I am marking the key words in the question. So let us read them one by one. So what was the Clausius statement? If you remember the Clausius statement, then you will automatically relate that which device was seen as the example of Clausius statement. So can you remember that we say that if you need to transfer heat energy from low temperature to the higher temperature, then it cannot happen automatically. You will need some work input, right? Then we also appreciated the example was what? Domestic refrigerator. So in which of the following devices will comply automatically? The option is domestic refrigerator. We learned this one, right? Let us go to the next. So some numericals, some small numericals means small. What do I mean by small? Means the calculation part is small, but conceptually sometimes good questions are also appearing in the PSU exams even. So let us solve this question. It says that there's a reversible Carnot engine. Mind the word reversible Carnot engine. And then it says that operates between 27 degrees Celsius and 1527 degrees Celsius and produces 400 kilowatt of net power. Mind the word what? Net. And then it says that the change of entropy of the working fluid during the heat addition process is. So it asks you that what is the entropy of the working fluid, what is the change of entropy of the working fluid during the heat addition process. So you will first have to find out that what is that amount of heat. See, what is this entropy is, what is this question trying to ask you is, see, there is some heat source and there is one sink. This is 27 degrees Celsius. This is 1527 degrees Celsius, right? And it says that it produces the net power of 400 kilowatt. So then his question is that the change of entropy of the working fluid during the heat addition processes. Then what happens is that there is some working fluid between these two, right? So working fluid is getting some heat from this one, and then that heat is converted into work, and that is the lower one is here. So he will ask you that what is the change. When the fluid was here, it has some entropy. When that fluid is here, it has some entropy. So what is the change in that entropy? So let us first try to find out what is the amount of heat, then only you will find out, right? So first you will convert these temperatures into what? Kelvin scale. So I am writing down the T1, this one as T1, this one as T1, and this one as T2, or T higher and T lower we have seen, but T1, T2 will also work. So this is 1527 degrees Celsius. So this temperature becomes 1800 Kelvin, and T2 is 27 degrees Celsius. So this becomes what? 300 Kelvin. Then what is the efficiency of this cycle? Efficiency of this cycle is 1 minus 300 divided by 1800, T2 minus T1. So this is 1500 upon 1800. So this is nothing but 5 by 6, right? Okay, so we also know this part that efficiency is equal to what? Work done divided by what was the heat supplied. So work done, in fact, work net. So here your 5 by 6 is equal to what is the W net given to us? 400 kilowatt and Q supplied. So here your Q supplied becomes what? 400 into 6 by 5. So 5, this is 80. So 80 into 6, 480 kilojoule. Okay. So now you need to find out what is the change in entropy. So delta S is what? ds, we know that ds is dq upon t. So q upon t. So what is q here? 480. And what is the temperature? That temperature T is at 1527. So 1527 means 1800 divided by 1800. So this will give you some value. Let us say this is 6, 8 times 6, 3. So 8 upon 30, this will be 0.266. See, this why we have calculated only for heat, this only for QH. Why? Because it says that change of the entropy of the working fluid during the heat addition process only. Okay, but it can also ask you that what is the entropy change during the overall process. So then what you will do, that initially you had entropy here, the value is given, and then you will be finding out that 80 kilojoule of heat is rejected. Okay, so 80 kilojoule divided by 300, this will give you another value. So this becomes the overall entropy change. This is the entropy change during the heat addition, but the difference between the here and here you have this much of entropy, here you have 0.266. So the difference between these two will tell you the overall entropy change. Okay, and this in fact will tell you the difference between these two is nothing but the entropy which has got generated. But since it is Carnot engine, so there will be no entropy generation. So this will again be same only. Can you see that 80 upon 300 here also we have reduced to 8 by 30 only. So this is 8 by 30 only. So can you see that since this was a reversible engine, then automatically I could see that there is no entropy what generation, the entropy change is same only, means the entropy remained constant. Okay, next. It says that uh, an engine works on the basis of Carnot cycle operating between temperature limits of 800 Kelvin and 400 Kelvin. Then if the heat supplied is 100 kilowatt, the output is, we don't need to pick the pen even. What is that which makes us not to pick the pen even? Why? Because you know that the supply heat, this is nothing but QH which we have seen, right? And what is the work output they have asked? So where we can see work output in the formula of efficiency. This is W net upon QH, and this is also equal to 1 minus T2 upon T1. Why I'm writing like this? Because it says that it's a Carnot cycle. Whenever we are talking about Carnot cycle, we can replace the Q with T also. So here your W net by QH, W net by QH is 100 is equal to 1 minus T2 is 400 divided by 800. So this is equal to what? Can you please solve it? Can you solve it? Yeah, 50. Okay, 50 is the right answer. Okay, let us go to solve the next question. Please solve this one. Okay, so let us read this question. It says that an engine operates between temperature limits of 900 Kelvin and T2. And then it says that the other engine operates between T2 and 400 Kelvin, and then it also says that for both the engines to be equally efficient, T2 should be equal to. So you need to find out if both the what engines are equally efficient, then what is this value of T2? So the given scenario to you is that there is one engine which has started operating from 900 Kelvin, and then you have one engine, okay, and then this is rejected to some T2, okay, T2, and then it has told you that Okay, then T2, and this is operating between one another engine and T2 and the 400 Kelvin. Okay, so we have one engine here, one engine here. So it output, some work output, then it tells you, it asks you that if the efficiency of both the engines are same, then what is this value of T2? So then what we will do, that we'll equate these efficiency equal to each other. So can you solve it now? So what will be the efficiency of 1, and it will be equal to the efficiency of 2. So efficiency of 1 is nothing but 1 minus T2 upon 900, and the efficiency of 2 is 1 minus lower upon higher. So this is 400 upon what? T2. So now you can cancel which one? This one and one got cancelled. This minus sign and minus sign also got neutralized. So can you see that T2 square is equal to 900 into 400? Then your T2 value is, you can find out. What is this? The square root of 900 into 400. This is 30 into 20, that is 600 Kelvin. Got the idea? Okay. So if you wish, you can, this is not big to remember, that sometimes they might ask you in the form of what? Notation. So here we have seen that T2 was nothing but square root of the upper and lower limits. Can you see? Can you see that this is nothing but the geometric mean even? So sometimes they might ask you questions in that form, that in terms of language also. So this will help. Okay, move to the next. It says that a inventor claims a thermal engine operates between ocean layers at 27 degrees Celsius and 10 degrees Celsius. Okay, then it says that it produces 10 kilowatt and discharges 900 kilojoule per minute. Such an engine is. It says that, is this engine possible or not? So let us try to find out if this engine is possible or not. So how you will find out the possibility of engine? That you will see, they have not mentioned that it is an what? Carnot engine. It says that somebody has developed an engine and which is operating between these two limits, and it also says that it has the this much of power. Then it asks you that if this is possible. So what is the idea to do is that, let us first try to find out its Carnot efficiency, and then we will find out the given cycle's efficiency, and we will look after that. If the both are equal, then we can say, or equal, or the what, the claim is, the claim which has been made, if the efficiency is lesser than Carnot, then also it is true. But if goes higher than Carnot, then it is an impossible case. So let us work up upon this one. So 27 degrees Celsius means what? 300 Kelvin, and 10 degrees Celsius means what? 283 Kelvin. Okay. And a engine, if this was Carnot engine, then it was the case. And now if you have been given the case of what, that you don't know if this is Carnot or what, but you know one thing for sure is that this is again 300 Kelvin. Here they have mentioned that it is 10 kilowatt. 10 kilowatt, it produces 10 kilowatt. So this is 10 kilowatt, and this is given as 9900 kilojoule per minute. So can we convert it into kilowatts? So this is 9900 divided by 60. So this will help you to convert into kilowatt. So what is 990 by 6? Can you solve this one? Okay. Then tell me what is the efficiency here. And here the efficiency is 1 minus 283 upon 300. This is equal to 17 upon 300. So you will find out that this is very lesser now, 0. 0.05 and 2206. So this is 0.056. Let us find out the efficiency of this one. So first you will have to find out 990 by 6. This is 165, right? So this is 165. So this is 10, this is 165. So this must be 175, okay? So efficiency will be what? You are getting 10 kilowatts. You are getting 10 kilowatts, and by supplying how much? 175. So what was the efficiency? Network upon heat input. Heat input was this one. And how I found out this heat input? Why? Because it says that it is discharging this one, this much, and it is producing this much, means the sum of these two must be here. Okay. So what is the value of 10 upon 175? So 10 upon 175 is 0.057. Okay. So 10 upon 175, this is 0.057. Okay. So can we see that these two are nearly equal? Right? So here your efficiency and here your efficiency, these two are nearly equal. So what we will say that this is an probable or possible. We can say that this is possible, right? So the best option will be possible one. Why? Because the efficiency is more or less very much close to each other. So this is possible. Yeah. Okay, let us read this one. It says that Carnot cycle consists of what? Two constant volume and two isentropic? No. See, this is very important, Carnot cycle. That is why I have included one question from this one. So we can see that the Carnot cycle consists of what was there? Two isothermal and two isentropic process. If you remember, two isothermal and two isentropic process. So this is just a recapitulation. Okay, let us solve this one. It says that dry saturated steam enters a frictionless adiabatic nozzle with negligible velocity at a temperature of 300 degrees Celsius. And then it says that it is expanded to a pressure of 5 megapascal isentropically, and the H2 value is this one. Then it asks you what will be the exit velocity of this steam. So first question or first thing which you should be thinking here is that where you have seen such and such data, or where you can find out the velocity. So velocity is the term seen in what? Kinetic energy, right? And kinetic energy and enthalpy, all these things were coupled where steady flow energy equation. So by using steady flow energy equation, we'll be able to solve this one, right? So let us try to solve this using steady flow energy equation. So what was a steady flow energy equation? Let me write the full one. So this was, what we can see is that it was q dot plus m dot into h1 plus v1 square by 2000, if you remember, plus g into z1 divided by 1000 here, 1000 is equal to W plus m dot into H2 plus V2 square by 2000 plus G into Z2 upon 1000. Okay, so this is the generalized equation, and those things which we are being given here, we'll consider those things for about which we have no data. Then what we will do, that we'll simply assume they are zero here. So we have seen that this is constantly mentioning us that this is an adiabatic nozzle. So there is no heat transfer. So this term is gone. And so nozzle, we know from our assumptions that it will produce no work. So this is also zero. And mass terms are only remaining. Then can I cancel out? Mass terms will also get cancelled out. Then it also says that with negligible velocity enters with, see, enters with negligible velocity. So what I would do is that negligible velocity means this is zero, and there is no mention about potential energy, so this will also get cancelled out. So what terms I am left with now, let me write those. This is H1 is equal to H2 plus V2 square by 2000. So by solving this one, you will got the value of V2. So V2 square by 2000 will be equal to H1 minus H2, and H1 is 2751 minus H2 is 2651. So V2 square is equal to 2000 into what? This value is 100. So now your V2 value will be square root of 2000, or this is 2 into 10 to the power 5. So yeah, this is 447.21. Got the idea? Okay. Let us read this question. It says that a reversible heat engine rejects 80% of the heat supplied during a cycle of operation. If the engine is reversed and operates as a refrigerator, then its coefficient of performance shall be. So here you have been given an engine, and when this engine is what? reverse to work as refrigerator, then it asks you what will be the coefficient of performance. So how you will do this, that how you will do this problem? First you will go on and find out the things about engine, and then you will go and find out things about the refrigerator, right? Then only you can relate. So here it is said that it rejects 80% of the heat. So if this is Q2, this is Q1, and you are getting some work W. So here you can see that Q2 is 0.8 times of Q1. Yeah. Then W is 0.2 Q1. Yeah. Then it says that if the engine is reversed and operate as a refrigerator, when you operate it as refrigerator, then what will happen, that you will provide, by reversing means what, that you will be providing it some 0.2 Q1, right? And what, here your Q2 is being what, removed from this place, and then this is rejected to Q1. So now your question is that, tell me what is the COP of this one. So we have seen already that Q2 was 0.8 Q1, right? So we know that if COP of refrigerator is what, the desired effect upon work input. So what was the desired effect here? Desired effect is 0.8 Q1 and your work input is 0.2 Q1. So this is 4. right? Yes. Okay. See, there is one formula. This is what I have tried to solve you conceptually, but there is one formula if you can remember. It says that COP of heat pump is equal to COP of refrigerator plus 1 is equal to there is some correlation between these two. So let us first try to find out what is that correlation. So can you correlate that? What is the relationship here? Can you correlate? Please tell me. This is nothing but 1 upon neta of engine. This is nothing but 1 upon neta of engine. Okay. So this is the relation if you can remember. Then you can also solve it through what? Through the concepts also. Okay. So you can cross verify it if you want to cross verify it, and you can cross verify it. Okay. So here, what is the efficiency of your engine? Your efficiency of engine is only 20%, right? Here your neta is 20% only. So here 1 upon 20% means 0.2 is 5. So COP of refrigerator becomes what? 5 minus 1 is equal to 4. Why? Because your efficiency is what? Efficiency is work upon Q supply, right? And work is here what? 0.2 Q1 only. So 0.2 divided by Q1, 0.2 Q1, and you are applying Q1. So Q1 got cancelled out. So your efficiency is 0.2 only. So if you divide it, put it here, this is 0.2. So this is 5 only. So can you see that COP of refrigerator is 5 minus 1, 4. This is the same as we have derived it here. Okay. Next question. It says that the efficiency of an ideal Carnot engine depends on what were the things on which this Carnot efficiency dependent upon the temperature of both source and sink. Why? Because the temperature of working substance or temperature of source and sink. Tell me. Temperature of working substance or working substance or temperature of source and sink only. Please think after. Between the limits only, right? Why? Because we have seen that it was not the temperature of the working substance, but the temperature of source and sink only, right? So here your option, best option is what? Source and sink only. Okay. This option. Next. It says that a insulated rigid tank is initially evacuated and the tank is connected with a supply line through which air passes at 1 megapascal. It says that the temperature of the air which is being supplied is 350 degrees Celsius. It says that a valve connected with the supply line is opened and the tank is charged with the air until the final pressure inside the tank reaches 1 megapascal. Then it says the final temperature inside the tank. So can you remember that I told you that TF was gamma times of Ti. So this gamma value is always greater than 1. So can you see that this 1 point anything, like let us say that it was 1.4. So 1.4 into Ti is always TF. TF is 1.4 into 350 plus 273. So can you see that this is automatically higher than 350 degrees Celsius? So can you see that is greater than 350 degrees Celsius. So there is no need to, if by sitting in the exam hall, for you it will be very difficult to solve, to derive that equation. So you will have to keep mind these things, okay? Then only we will be able to solve the questions in the exam. Let us read this question. It says that the correct statement regarding the entropy is that entropy is a path function. Was entropy a path function? No. Why? Because entropy is a property. Why? Because it's a property. Entropy is a property. Right? So this statement is wrong. Then it says that entropy can be obtained from a direct measurement of Q and T. So can you tell me that entropy can be obtained from a direct measurement of Q and T? Only Q and T will not help you. Why? Because we have seen, this is not telling you to find out that, yeah, we have seen that ds is dq upon t, but there was delta s which was being generated. This term is also there. So only dq upon t data will not be able to help you. So this option is partially incorrect. Okay. Then it says that during a change of state of the system, the entropy change is the same whether that change has occurred via a reversible process or an irreversible one. It says correct statement. Why? Because the entropy is a property. So if the one point is here, second point is here, doesn't matter that if you have gone reversibly or if you have gone, let us say, irreversibility. Because if you have reached from 1.1 to 2, then you can always say that this is correct. Okay. And entropy of an isolated system is zero. This is also not the correct option because we have seen universe is an isolated system and the entropy of isolated system is greater than to zero. Okay. Let us read this question. It says that when a system undergoes a process such that dq upon t is equal to 0 and delta s is greater than 0, then the process is. So let us first try to find out the equation of entropy change. So this was ds is dq upon t plus delta s of generation. So, but it has says that the cyclic integral of dq upon t is 0. If this value is 0, but it has says that ds is greater than 0. That means delta s generation, this value is greater than 0. And if entropy is generated, then that process is nothing but irreversible. Right? But if dq upon t can be 0 only when your this term has got what change, zero value, right? So can I say that if dq is 0, see, I am telling you a general term, like let us say that ds is dq upon t plus delta s generation. So if I say that if it is adiabatic, then I can clearly say that this value is 0. Then if this is 0 and if I say it is irreversible, then can I say that ds is greater than 0? So this is the case that this process is irreversible and adiabatic. So irreversible and adiabatic. Okay. Next question. It says that a ideal gas of mass m and temperature T1 undergoes a reversible isothermal process from an initial pressure P1 to final pressure P2. Okay. The heat loss during the process is Q. Then it says that the entropy change delta S of the gas. So basically he is interested in delta S of gas. And what is the given data? It says that it's a reversible isothermal process. Okay. So one thing, and it has given data about pressure. So there is one more thing. So can you remember that delta S of gas, delta S of ideal gas, in fact, this is ideal gas. Okay. So this was mcp log of T2 upon T1 minus R ln P2 upon P1, right? But since it is an isothermal process, so this term will be directly 0. Then this is the only term left. So this is minus r log of P2 upon P1. So can you see that mr into log of P2 upon P1, this m is also multiplied here now. So this mr log of P2 upon P1 is also given and in the option 1 itself. But can you see that your final solution is having negative sign with it? That means if you take it with the log, then it becomes mr ln P1 upon P2 instead of P2 upon P1. So the option B is correct, even though this says the same thing, but since there was a minus sign, if the minus sign they have mentioned, then this was correct. But since they have not mentioned any sign here, that means you will have to take care of this sign as well. Okay. Next question. It says that a heat engine, the Clausius inequality we have seen. No? So this question is based on that problem. Okay. So it says that a heat engine receives half of its heat supply at 1000 Kelvin and remaining half at 500 Kelvin. So what is this question is that there is a heat engine and it receives half of its supply at 1000 Kelvin and remaining half at 500 Kelvin. Okay. So if this is 1000 Kelvin, then it is here, and another one is 500 Kelvin. So this is getting this much heat. Then it says that heat is rejected to sink at 300 Kelvin. There is one sink at 300 Kelvin. Then it asks you the maximum thermal efficiency of the heat engine will be. It says you that what is meta max. So here you need to what take care of few things. So it says that half of the heat is coming from this side and half of the heat is coming from this side. So what is the efficiency? So do you remember that cyclic integral of dq upon t will be equal to 0? Can you recall that? Yes. So we'll use here only. So here let us say this is Q1, then Q1 by 2, and this is also Q1 by 2. So can you use this concept that dq upon t is equal to 0? That means Q1 upon Q1 by 2 divided by temperature is what? 1000 Kelvin. 1000 Kelvin plus this is also Q1 by 2 upon this is 500 Kelvin dq upon t is equal to 0. That means you are rejecting some heat here, right? Let us say that this is the Q2 value or Q rejected. So minus Q2 upon, can I write down this value is given as 300 Kelvin upon 300 is equal to 0. So here by solving this one, you will find out the relationship between what Q2 and Q1. So can you find out the relationship between Q2 and Q1? So can I use this concept that this is Q1, or instead of taking 2, what I am doing is that let me say that this is Q and this is Q and the total one will become what? 2Q. Okay. So can I use this concept? Then can I write down Q upon 1000 plus Q upon 500 is equal to, I'm taking this one on the positive side. So QR I am writing Q rejected upon 300. So this is gone. So can I see that this is 0.1 Q and this is what? 1 by 5 is 0.2 Q, right? Is equal to Q by R to multiply whole this term by 3 is equal to QR. So can I see that QR is nothing but 0.3 Q into 3? This is 0.9 Q. So you are receiving how much heat? You are receiving total heat as total heat supply is 2Q, and total heat rejected is heat rejected QR is 0.9 Q. So work done is what? 1.1 Q. So what is efficiency is 1.1 divided by 2. Can you solve this one? So this is 0.55, right? So 0.55 means 55%. So see, this is in option 1. See how I have utilized the information here. So let me tell you how I have utilized the information. Oh, let us. Okay. So what I did assumed is that if this was the given scenario, I hope you have appreciated. If this was the scenario, then I received Q from here, Q from here. Why? Because it says that 50% means equal amounts from these two, and then you rejected some QR here. The temperature was given 300 Kelvin. This was, let us say, 500 Kelvin, and this is 1000 Kelvin. So I am using the Clausius inequality, that is dq upon t is equal to 0. Is what does it mean? That what is the heat coming from here and from here, and this is going outside. So why I am taking this one as plus? Because this is coming to this point and this is going from this point. So Okay, so it says that the availability of system at any given stage is, what is the availability of a system at any given stage? So let us read them one by one. So is it a property of the system? No, definitely not. And then is the total energy of system? No, it is not the total energy, but it is the that part which is the maximum work which is obtainable when your system goes to the dead state. So the best option is what? That it is the maximum work obtainable as the system goes to the dead state. So what is the best option? Option C. It says that the maximum work obtainable as the system goes to the dead state. But see, there is one more option which says that the maximum useful work. So is it like that maximum useful work? No. Why? Because this system will give you, or this the availability will tell you that what is the maximum work which you can get. Okay, and what is the useful out of that, you will have to think after. Okay, maximum useful may be equal to available, maybe less than that, but that doesn't affect your available energy. Okay, see, the difference between these two is, when we will extend this study further, then we will appreciate. But as of now, what we can say is that the availability part, it says that what is the maximum in obtainable work, like what is the maximum work which you can obtain when your system goes to the dead state. Let us say that you have got W max, but out of this W max, what is useful, it is not the concern of W availability. This is up to you that how you can make the most of them useful. But the maximum work which is obtainable at dead state is called what? Availability. Okay, now. So it says in the next question that which one of the following represents unavailability? So do you remember that W max we found out, or W available energy, we found out that it was W minus, or in fact Q minus T naught into delta S. Do you remember? So this T naught into delta S we named it as unavailable energy. This we have seen, right? So this is unavailable energy. So which option suits the best? Which is unavailable energy T naught into delta S, right? So this option. Okay. Let us move to the next. So let us now study something. Why? Because we have solved ample amount of questions based on second law of thermodynamics, and also we have seen steady flow energy equation. We have also seen questions on means basic concepts of availability and non-availability. So let us now move to whom? Let us now move to how to define or determine the availability of any given substance. So this is done as follows. So let me first write down the availability part for the given scenarios. So we have seen the availability part when it was a what? Engine. For any engine we have seen, right? So let us now write for whom? Let us now write for solid substance and gaseous substance. Okay. So available energy. So available energy, we have seen that we have three cases. Available energy, we have three cases. First case is thermal energy at constant temperature. constant temperature. And then we have the case of what? First case we have seen is that W, or in fact available energy, was nothing but Q into 1 minus T naught upon T, and then we changed it into what? Q minus Q upon T into T naught. Then we say that this is Q minus T naught into delta S, right? We have seen this one, available energy. So if this is your part, then what happens is that if this is your nothing but engine working between two temperature limits, right? That because your thermal energy is at constant temperature. So let us say this is T1 and this is here for now this is T naught, right? So not T1, let us say T only. So available energy is Q minus T naught into delta S. So the next question which we have seen is that useful word we have seen, right? So W max is this one, this available energy. So out of this W max, what is useful? So in this case, there is no atmospheric work involved. Why? Because this is the working system which will not involve any uh, surrounding work, right? Like no interaction with the atmosphere. Why? Because this is an engine installed between two temperature limits. So your W max useful will be nothing but available energy, or I can say that this is W max itself. Okay. Then we have another case that they will ask you what is change in available energy. Change in available energy, what does it mean? Let us say that you were having temperature T1 and then you reach to T2, but this is not equal to the atmospheric temperature. Got the idea? Like you were working between T1 to T2, but this is not the T naught, right? So how I will write down here you have some energy, right? And here you also have some energy. Why? Because this has not reached T naught. So the difference between these two is nothing but change in available energy. So what will be change in available energy will be Q into 1 minus T naught upon what? T1, the initial one. Why? Because this is the energy which you have at this point, and then you have reached to this point. So this is Q into 1 minus T naught upon what? T2. So this is how you write change in available energy. But if you wish to write only available energy, then what you will do is that available energy is Q into 1 minus T naught. Let us say that if this temperature is T, then this is like this one. Okay. Next. Then sometimes we have substances, like one case we have seen now that finite body, sorry, not finite body, thermal energy was at constant temperature. And then you can have the finite body, like let us say solid or liquid. Then you will ask me that what is the available energy with this solid. Similarly, you will ask that what is the available energy with the gas. So for finite body, body, you have the case where you deal with solid and liquid, and you have one case where you deal with whom? You deal with gas. Okay. So with solid and liquid, what is the availability function? See, have you seen that the availability function was nothing but available energy? Can you see that this was the available means maximum energy which you had minus of T naught into delta S, right? So this we have seen in case of what? The means the reservoirs were at constant temperature. Okay, but now I am talking with solid and liquid. So here your available energy will be function of whom? Because there is no flow, that means you will be having some internal energy, again minus T naught of what? S. or delta S, why I'm writing that notation is like this one, but you can write S also, no problem. Okay, so available energy is function of U minus T naught S. Got the idea? This is the energy, maximum energy you can have, and this is the unavailable energy associated with it. So what is the available energy at a point? Why? Because you need to subtract this one from atmosphere also. So why? Because you will have to counter that when you will reach the dead state means atmospheric state, then what will be the energy associated with you? So the energy associated with you will be nothing but you if I name it as that this is my availability function, then change available energy at a point will be what is my energy at the given state minus what will be the at the dead state. So phi 1 is nothing but u1 minus t naught s1, and what is phi naught? Minus of u naught minus t naught s naught. Okay. So your availability function is U minus T naught S, and when what is the available energy at a point is the available energy at that particular situation minus of the available energy at what? Dead state. The difference between these two is nothing but available with you. Okay. Similarly, what will be the change in available energy? Change in available energy, I can write down that this is nothing but you have started at 1 and you have reached 2. Here what we have done is that we have started at 1, reached to the dead state. And why I am writing like this is that this is the energy associated with you, but out of that this is not available with you every time. Okay, so that is why this becomes availability function, and available energy at a point is the difference between you at this point at point 1 and the same. So the change in available energy becomes what? Phi 1 minus phi 2. And how can I write this one in? This is u1 minus t naught s1 minus of u2 minus t naught s2. Mind the words here, I have used u naught. Why? Because I was talking about phi naught. But is there any again atmospheric work involved? No, here also there will be no net atmospheric work involved. So this is itself the maximum useful one also. This is the maximum one and maximum useful also. That means this is the maximum one and this is the maximum useful also. Okay. Let us now go to gas. What will happen with the gas? That can I write down that change in available energy will be U1 minus T naught S1. Change in available energy, from here I am directly taking that this is U2 minus T naught S2. But when you are working with the gas, that means you are compressing it, expanding it. So what will happen? The piston, while moving from expansion to compression, compression to expansion, there will be atmosphere outside it. So during expansion, this work will also be involved. Which work? The atmospheric work. So even during the compression, atmospheric work will be involved. So what you need to do now is that you will have to take care of that. What? The atmospheric work which is involved. So what I would do is that I will involve what? Take the difference of atmospheric work, and atmospheric work is happening at what? Constant pressure. So this is minus of P naught into V2 minus V1. Got the idea? Why I am using is this, that when your working substance will be gas, then how you will take the work out of gas? You will put it into piston cylinder assembly, and then you will let that gas expand, then your volume will get changed. But this volume change, during the change, let us say that this is the scenario, and if this piston is moving upwards, then it has to work against the atmosphere also. Why? Because it is trying to push the atmospheric gas from this point to this point, or whatever was the limit. So that means you are working against the atmosphere. So this work is not available with you, right? So you will have to take care of this one also. So now can you see that your change in available energy is U1 minus T naught S1, and this minus P naught V1, this is minus P naught into minus V1. So this becomes plus. So can I write down this is P naught V1 and minus of U2 minus T naught S2, and again this is minus. So this is minus P naught V2, minus we have already taken care, so I can write it with the plus one. So if even if you open this sign, the same thing you will get. This is plus P naught V1 plus P naught V1. This is minus P naught V2. This is minus P naught V2. So no problem at all. So here can you see that this is your availability function. This is your change in energy. So what is your availability function now? This one. So if I wish to write the availability function for gas, then my availability function for gas, can I write down, this is U minus T naught S, T naught S plus what? P naught into B. So this is your availability function, and this is availability function. So T naught S naught P naught V naught I can write, because I will be writing with respect to whom, that if you are able to reach the dead state. No, like phi of the gas. So sometimes they will ask you that what is phi of gas. So this is even if you don't remember this one, like you can remember this is also true. So even if you don't mind, then phi availability function is this one, and this is for whom, phi of gas, and phi naught, rather phi naught, then phi naught is u naught minus t naught s naught plus p naught v naught. So phi naught value is this one, phi is this one. So your availability function is u minus t naught s minus p naught into v. Depending upon where you are, you use the notations of u1 s1, u naught s naught, right? Because we have seen now, then when we were at u, we used u2 minus t naught s2, p naught v2, like that. Okay. So here your W max useful is W max minus W atmospheric. Why? Because you had to counter this one. So can you see that there are instances where your W max useful is not equal to the available energy, but available energy minus of atmospheric work. Okay. And now what is the third case? Third case is when you are working with flow process. Let us say that there is a substance, or let us say this turbine in which there is some steam which is entering into it, then how you will take care that what is the available energy with that particular steam at that instant. Then what you would do is that you will counter it into whom, into flow process. Then when you are working with flow process, then what is the available energy with you? Your available energy with you will be the, what is your enthalpy minus of T naught into S at that particular instant, and plus of C square by 2, means the velocity by 2, means I am writing down, this is nothing but the kinetic energy. If you confused, let me write it V only. So why I am writing down C instead of V is that not to confuse with the volume. V square by 2 is the kinetic energy plus potential energy. See, so I have only written this one again, that minus of T naught S only, but I am not subtracting anything from it. Why? Because the kinetic energy and potential energy are fully available energy. There is no unavailable part into it. If you wish to convert this kinetic energy into other form, then it will get fully converted. So it doesn't mind, there is no unavailable part into it. But these things have got unavailable part. So that is why And when the flow was happening, then what is the energy associated with u is enthalpy only, right? And when there was no flow, that means the case of, you can say, a closed system. So what was happening there, that you were having internal energy only, no enthalpy. Okay. So what you would do is that available energy at a point will be again what? That let us say you were at phi 1 minus of what? Phi naught. Yeah. And what will be the value of phi naught? If you have reached to the dead state, that means there is no velocity and there is no potential effect even. So if you have reached to the dead state, that means phi naught, then your phi naught will be h naught minus t naught s naught. What the idea? Okay. So this is all about available and unavailable energy. Okay. And if someone asks you that what is change in available energy, then what you would do is that phi 1 minus phi 2. Okay. Let us go to the next. Next is irreversibility. Sometimes they ask you to quantify this term. What is the amount of irreversibility? Okay. So irreversibility is I. This is equal to T naught into delta S, which is generated. So you won't think anything about irreversibility if they ask you that what is the quantity or what is the irreversibility associated with the process, then you will directly write down that irreversibility is T naught into delta S generation. Okay. And this is given by whom? Gauss-Stodler. Okay. And now, sometimes in the PSU exams, we have seen this various times, that what are the causes of irreversibility. So let us understand what are causes of irreversibility. Causes of irreversibility. So first, very obvious cause is that when you are conversion of high grade energy conversion of high grade energy into low grade energy. Okay, this is one. And what are the causes of this irreversibility? One is friction. Like when you are working with the change of high grade into low grade, then there can be frictional effects, there can be viscous effects, there can be elastic collision, inelastic collision. Inelastic collision means what? There is some loss now. So those things who are causing some loss and those loss are irreversible, then we name it was that it is an cause of irreversibility. Let us see one example. Let us say that friction. Let us say that you were working on substance and then you have some frictional loss. So let us say that this was 10 kilojoule. But this will never happen that if you reverse this one, like if you supply the lost 10 kilojoule of heat, then this will never happen that your body will start movement. So that is why we name the frictional loss as irreversible ones. Why? Because the vice versa is not true. Like frictional loss is converted into heat, but if that heat is again given to that particular object, then this will not get converted into what? That other form of energy. Let us say that it will, if you supply the heat to this object, then this will never move, but during this movement it has lost some energy. So that is why I am naming as friction as irreversible loss. Viscous forces are causing what? Viscous forces are causing what? Frictional losses.
means irreversibility, and in elastic collision again there is some loss, and flow through electrical resistance there is always some loss. Got the idea? Wherever you are facing certain kind of loss, and that loss is not reversible, that means that if you reverse the process, like if you have lost something and if you apply that lost one, then it will not ever happen that the lost one, let us say for example, the heat is not moving this object. Okay, so that is the idea. And next is, one cause is that conversion of high grade into low, and the second important cause is heat resistance through heat transfer heat transfer through finite temperature difference, heat transfer through finite temperature difference. So what does it mean? See, let us say that you are working between two temperature limits. You have one engine, and then if you are not working with equilibrium states, then what happens is that, let us say you are at 1000 Kelvin and then your heat is at 500 Kelvin. Then what is the delta S universe? Let us say that you are traveling, your not engine is there. Let us say that for simplicity, let us say that 1000 kilojoule of heat is being transferred from 1000 Kelvin to 5500 Kelvin. Then what is the delta S? Delta S of universe will be nothing but dq upon t. So this is 1000 is at 500 now, but this 1000 was initially with whom? 1000 Kelvin. So this is equal to 1. But can you see the same delta S universe when I reduce this temperature? So let us say that I am transferring this 1000 kilojoule of heat from 500.001 to 500, then can you see that this delta S universe value is very low, right? Like it's equivalent to 0, but here you have got some value, right? So can you we see that whenever there is a finite temperature flow through a finite temperature difference, then can you see that this delta S universe was not equal to 0? That means some entropy has got generated. This delta S universe is nothing but the entropy generated. So entropy generation means what? Entropy generation means irreversibility, right? So that is why this is the thing causing irreversibility. What is that? Heat transfer through finite temperature difference. Okay, then this free expansion we have seen now, free expansion or unrestrained expansion, expansion against vacuum. So free expansion is also causing very high level of irreversibility. This we have talked. Okay, and then when you are mixing two dissimilar substances, mixing of two dissimilar substances, if you are mixing two dissimilar substances, then you will always be having what? Certain irreversibility associated with this. So many a times they have asked us that what is the which of the following is the cause of irreversibility. So you should be careful looking at the options. Okay, now let us now move to very important part with respect to PSU exams, which is properties of pure substances. Properties of pure substances. Properties of pure substances. So what do we do here is that we try to find out like properties of pure substances means what, that there is only one substance which we are talking about, means pure substance means what, that the homogeneous mixture. Do we remember? We are talking about homogeneous mixtures only. We'll never talk about non-homogeneous mixtures. Okay. So here what we are going to study is that what are the interrelationship between the properties. Let us say that we have temperature, pressure and volume. So is there any way that if I know any one of the temperature, pressure or volume, or then can I find out the another one? And the most important is that what is the variation of one property with respect to other. So this is the need of this chapter, which says properties of pure substances. Okay, so let me draw one very basic curve used in properties of pure substances is this way. Okay, so I'm drawing it here for temperature and entropy axis. So I am helping you to understand that what I am trying to say. See. See what happens is that your general substance has what? Some, let me tell you again. See, I'm drawing one curve. So what happens is that you have initially solid region, okay, and then you have liquid region. This is your liquid region, and this is your solid plus liquid region, and then you have vapor region here, vapor region, then you have liquid plus vapor region here, and if this is solid, this side is vapor, then this is your solid plus vapor region. So this point is nothing but the triple point of this. I have drawn for whom? For water. This I have drawn for whom? For water. So for water, can you see, or for any substance, this triple point will signify whom? That all three phases are coexisting in equilibrium. Can you see that there is one S, there is solid region. Yeah, this is solid region. Can we see any liquid region? Yes, liquid region is also there. Can we see any vapor region? Yes, solid, liquid, vapor, all three are coexisting at point. Then that is why we name this point as what? Triple point. Okay. Okay, now. So most of the time what we are worried is that liquid and liquid plus vapor region and vapor region. Why? Because when you are working with turbines, when you are working with Rankine cycle, where which is used in turbines. So we are mostly using whom? Liquid and liquid plus vapor region. Why we are not worried about solid region is that solid region is our of no use. Why? Because we cannot take work out of solid regions, right? Liquid and liquid plus vapor region, or more probably vapor region, is always giving us some work, but solid, why? Because solid needs some flow, because whenever obtaining some work you need flow. Why? Because we have seen in practical devices we were talking about enthalpy. Why? Because there was some flow. So solid regions we are not interested, because in order to make solids flow we need very much of work itself. Okay, so that is why we are not worried about this region much. So if I take this part only, means liquid and liquid plus vapor and vapor. So these are called what? Phase change region. These are phase change regions. Why? Because here your liquid phase is there, here your vapor phase is there, but inside this dome we can see that liquid plus vapor are coexisting. That is why this region is named as phase change region. Okay. Now, so when I draw this one, this was drawn on whom? This is drawn on TS scale. Okay. Now, if I draw the same curve only for liquid and vapor region, then this curve would be nothing but I would eliminate which one? The solid parts. Okay. So this is your dome. Now what happens that this is your temperature axis and this is your entropy axis. So this is your phase change region, also called what? Wet region. Okay. So these graphs are what? These graphs are experimentally determined. This is not like that you have uh, determined it with some formula or something. No, this is always drawn through whom? Through the experiment. So the experimental data are plotted and they look like this one. So what does it mean that at this temperature and this entropy you are at this situation, when then it says that at this temperature, this entropy, you are at this situation and like that. Okay. So this is wet region. So now let me help you to draw the pressure is equal to constant curves in onto it. Why? Because you need to find out the correlation between these two, right? Like on TS axis, what will happen when your pressure is constant, how flow would look like? So if your pressure is constant, so your flow must have started from this one. Then what happens that this is your liquid region, this is your vapor region, and this is your liquid plus vapor region. Then what happens that your flow has started somewhere, and then when you have started boiling it at some constant temperature, sorry, pressure, constant pressure means what? That you can examine, you can assume it like you are boiling some water into your pan. So what happens that with the increase in temperature, your you are shifting towards whom? Vapor change region. Can you see that when you uh, boil your water in a pan, then what happens that it starts boiling, and then it's initially what you can see is that there is no boiling. Initially you can see that it has absorbed heat. So this is that reason where I cannot see any vapor region. Then I start looking some vapor forming it, and then after some point the all the liquid has evaporated into vapor. So here your only liquid was existing. After this point there was liquid plus vapor region, and if you heated it more further, then you will find out that it has completely got converted into vapor region. Then it was found that during this heat, this is your pressure is equal to constant curve. So what happened that when you entered into phase change region or wet region, then it was found that there was no change in temperature as well. Like what happened that if you kept on heating, then once the boiling starts, that means once the phase change starts, then your pressure was constant already, but your temperature also became constant. For whom? For phase change region. Okay, so can we say that during phase change, temperature and pressure are very dependent properties? This will never happen that if you are working at some pressure, then this temperature is always unique at which this starts boiling, and this is also remaining constant. Got the idea that at what temperature it would boil, this is fixed, and during boiling this will remain constant. These two things are always fixed. So can we say that at every pressure there is there is one unique boiling point? Okay. So from childhood, since childhood, we have heard this sentence that the boiling point of water is 100 degrees Celsius. So this is partially correct because you will also mention that this 100 degrees Celsius is at what pressure? So 100 degrees Celsius at 1 atmospheric pressure, the water starts boiling. Then somebody would ask that is there any possibility that if I am at 1 atmospheric pressure, then is there any possibility that before reaching 100 degrees Celsius, it will start boiling? So yes, it can. What you can do is that if you decrease the pressure, this boiling point will also decrease. So this can happen that if you decrease this pressure more further, then what will happen that your water will start boiling even at room temperature. If you decrease the pressure, if pressure decreases, then we can see that the water starts boiling even at room temperature. Okay, so this was it. Then there is question that if you increase the pressure, like let us say that this is P1, then if you increase the pressure, how it would look like that this has work something like this. Let us say that this is P2 is equal to constant. So if you keep on increasing this pressure, then can you see that you will reach one point where there is no change in uh, like there is no wet region, right? This wet region has got eliminated once you have reached this point. Then what happens that your liquid has directly flashed into vapor region where there is no phase change. So can I say that there is one unique point existing which is converting liquid directly into vapor? So this point is called what? This is called critical point. Got the idea? Critical point is different and triple point is different. Triple point, what did I told you? That triple point is that where all three phases coexist in equilibrium, and critical point is the one where liquid directly flashes into evaporator. Okay. Then let me erase some part from it. Let us only keep this curve and okay. Okay, now. So this is called saturation temperature. Why this is called saturation? Because this is the point where liquid has started converting into vapor. So this is called saturation point. So the liquid, this is the liquid. Yeah, this is the reason where liquid is below saturation or saturation temperature. So the liquid which is present below the saturation temperature is called subcooled liquid. So this region is called what? Subcooled, subcooled liquid. Okay. And when you have reached this point, let us say that your liquid is lying at this point. And what you will name them is saturated liquid. Why? Because you have reached the verge of what? Saturation. So this is called saturated liquid. Understand the difference between these two, that when you are below this region means that you have not started boiling, then you will name it what? Subcooled liquid. When you have just started boiling, then you will say that this it has got saturated. Okay. Then let me say that this is your temperature T1 and this is your temperature which is T saturation. Then there is one term defined which is called degree of subcooling. Degree of subcooling. So what is degree of subcooling? This is the difference between these two temperatures. So this is equal to saturation temperature minus of T1. Okay. T1 means T1 can be anything, like even if you are here or anywhere, so you can name them as T1. Okay. So degree of subcooling. So till now what we have studied is that what is subcooled liquid, what is saturated liquid, what is degree of subcooling. Okay. And then you have reached this point. Okay. So this point, this is the point, like even if you cool it by very minimal amount, then what will happen? It will start condensing, right? Like it will enter into wet region. So this is the point where your liquid is just about to get condensed, like not liquid, vapor. Like liquid cannot condense, na? So where the vapor is just about to get condensed, then we name those as saturated vapor. So this is saturated vapor. Okay. And any region beyond this point, like this region is called what? Superheated. This is called superheated. So let us say that you are at this point, but I'm not telling you that you can at this point only, like wherever you are lying on this line. Like if I say that this is where you are lying, this is where you are lying, you can lie anywhere, right? So that is called superheated region. Then there is one again term defined, degree of superheat. Degree of superheat. So what will be degree of superheat will be T2. Let me say that this temperature is T2. So this is T2. So T2 minus whatever was the saturation temperature. So can I say that degree of superheat is T2 minus T saturation? So hope the idea of saturation, temperature, pressure, and degree of superheat, subcooling, these things are clear. Okay. So this part, like this part which I am making red, can you see that this is the phase change region? So this is the amount which is called what? Latent heat. What is it? This is latent heat. Latent heat bonds, that hidden heat. This is the amount of heat which will be required for you to supply. Like let us say that here your enthalpy is H1, or and here your enthalpy is Hg. Okay, and let me tell you that this is Hf. So this is Hf and this is Hg. Then what is the latent heat? Nothing but Hg minus Hf, the difference between what? The enthalpy at this point and enthalpy at this point. This is called latent heat. So can you see one very important phenomenon about latent heat? What is that? That latent heat is decreasing with the increase in pressure. Can you see that when you are at P2 and P2 is greater than P1, then can you see that this difference has got reduced compared to this one? And when similarly you are moving towards the critical point, then can you see that this latent heat is decreasing? So latent heat decreases, latent heat, what I can say, decreases with the increase in temperature, sorry, pressure, with the increase in saturation pressure. Okay. And can you see that this value is 0 at critical point, and it is equal to 0 at what? At critical point. Okay. So at critical point, this is 0. And can we see that there is no latent heat? And this is more specifically called what? Latent heat of vaporization. Like this is latent heat. I told you that this is the hidden part of between phase change. So here we are converting liquid into vapor. So this is now, you can understand that this is latent heat of what? Vaporization. So this is latent heat of vaporization. Okay. Now, this is too much into this slide, so let me erase something. Oh, let me erase the folder. Okay. So now, can you see that? Can you see that in this TS curve? In the TS curve, if you are like this one, then your critical point, your critical point, there is no latent heat of vaporization. And one more thing, that critical point is a fixed point. So its degrees of freedom of critical point will be what? 0. That means it is a fixed point. And for water, this is important. Sometimes we have seen the questions based on this directly, that what is the critical point of water? They ask the numerical value. So this is 374.16 degrees Celsius. This is temperature, and pressure is 221.6 bar. So this we should keep in our mind. Like for water, what is critical point? The temperature is 374.16 degrees Celsius and the pressure is 221.6 bar. So this point will be always fixed. Okay. Then one more thing, like when you are started movement from this one and then you got into the wet region and then you have reached this one, then there is one important term called dryness fraction. Dryness fraction. So this dryness fraction, it is equal to mass of vapor upon mass of vapor plus mass of liquid. So tell me, is there any dryness fraction at this point? No. Why? Because there is no mass of vapor. Here there will be mass of vapor and mass of liquid both. So dryness fraction is defined in this region. And there will be any dryness fraction here? Yes, there will be dryness fraction, but this will be always equal to 1. Why? Because there is no liquid. So here your dryness fraction is 0. And here at this point you have fully vapor only. So your dryness fraction will be what? Always 1. So you have started your journey from 0 to 1. So what is the limit of dryness fraction? This denoted by X will started its journey from 0 from here and from 0 to 1 at this point. Okay. So this is mass of vapor region plus mass of vapor plus liquid. Okay. So dryness fraction I can write. Okay. So sometimes this dryness fraction is the only key which will help you to determine the, let us say that they will ask you what is the volume here, what is the enthalpy here. So, and if you know the dryness fraction, then you can find out directly by whom? Directly if you know the enthalpies at this point, entropies at this point and other things. So that is why it becomes important to derive this part, that how to find out the enthalpy, entropy and other properties in this region. Okay. So can we see that that volume whatever will be here, the volume will be equal to what? Volume of vapor plus volume of liquid. This will be there. Yes. And volume of vapor is, can I write down? This is, or let me write down the specific volume. So specific volume of vapor is volume of vapor per unit mass of vapor. Can I write? Similarly, specific volume of liquid region is volume of liquid region upon mass of liquid. Can you see that when I am using a specific word, then I am using the notation in terms of small numbers. Okay, so this is a specific volume, this is a specific volume of vapor, a specific volume of liquid. So can I write down that this volume, and what about a specific volume of the entire substance? A specific volume of this entire region will be volume divided by mass of vapor plus mass of liquid. Yes. So now can I write down this term that I can write now that specific volume into mass of vapor plus mass of liquid, that means this is the volume, is equal to volume or specific volume of vapor region into mass of vapor region plus specific volume of liquid part into mass of liquid part. So can you write down this V is equal to V of V into mv upon mv plus ml, and similarly this is VL into ml upon mv plus ml. So can I write down this one as, this is nothing but dryness fraction, right, x, and this is nothing but 1 minus dryness fraction. So 1 minus dryness fraction. So can I write down that if I need volume part, then I can write down that V of V into x plus V of L into 1 minus x. So can I write down this one as VL? Like if you expand this one, then volume is V of L. Why? Because VL into L, 1. VL into 1 is nothing but VL now. Plus, can I write down this is minus x, right? So if you take common x, then this is V of V minus V of L. So this is the formula of what? Volume. So based on this fact, what I have done here is that volume of liquid plus x into difference between volume of liquid minus vapor. So when you will be asked now that tell me the density, then density is 1 upon rho. So this will be 1 upon rho L plus x into 1 upon rho G minus 1 upon rho F. So I am using this one as G and this liquid term as F. Okay. So based on this fact, I can write down any property. Let me say that if I am desired of U at any particular point, so I can write down U is UF plus X into UG minus UF. Simple. Similarly, if I need H, then how I will write? H is HF plus X into Hg minus Hf. Similarly, if I decide to write what is entropy, so this is Sf plus X into Sg minus Sf, and like that. So what are these things? Let us say that if you are given with any phase change region and you know the entropy at this point, enthalpy at this point, and what internal energy at this point, and you know about the gas also, so you know about the liquid, you know about the gas, or let me use that F fluid. Okay, so if they ask you that, tell me that what is the enthalpy, entropy and energy here, what is enthalpy, entropy and internal energy here, what is enthalpy, entropy and internal energy here, so what you will do is that you will find out X. Once you find out X, you know SF, and if you know SG, then you can find out this one and this one. So this G minus F part is also summarized as what? I can also write this one as HF plus X into G minus HF as HFG. Similarly, this I can write down as SF plus X into SFG, and like that. Okay. This is very important. Sometimes we have seen directly they would give you the values between these 2 points, and they will ask you that if the um, X value is this and this, then they will ask you that tell me what is the entropy and other regions. Okay. So now I can write down enthalpy and entropy at any point. Can I write down enthalpy and entropy at any point? Yes. So let me help you write down enthalpy at various point. So when you are in wet region, let us say, let us go to the next slide. Let us say that you are having any flow and you have obtained these characteristics. Let us say that okay. Okay. So if this is again TS, then let me say that somebody ask you that what is H1, somebody will ask you what is H2, somebody will ask you what is H3. So in wet region, in wet region means in this region, what is enthalpy? Let me say that H1 is equal to what? If this part is, I have told you this part is Hg and this part is Hf, right? So H1 is equal to Hf plus X into Hfg, right? No problem at all. And this Hfg part is also called latent heat. This we have appreciated. Okay. And when you are in superheated region, let me say that you are deciding with H2, then means in superheated region. So in superheated region, H2 is equal to what? So have you remembered this thing that dH was Cp dt, right? And this is applicable when your pressure is constant. So on this curve, pressure is equal to constant. And if I desire the enthalpy at this point, then can I write down that this is nothing but dH is nothing but, or if I wish to write H2, then can I write down that H2 minus Hg is equal to Cp into dt. Dt means what? T2 minus T at G, or this is also saturation temperature T saturation. So H2 minus Hg will be equal to Cp into T2 minus this one as T saturation. Okay. And now what about subcooled? This is subcooled region. This is superheated region. So in subcooled region, what happens in subcooled region is, can I write down that HF minus H3, HF, see this is HF minus H3. Why I'm writing like this? That this value comes later, na? Then this will be higher. So HF minus H3 will be equal to Cp into T saturation minus T3. But can you see that one more thing, that your Cp and Cp value, if this is not constant, like Cp value can get changed in vapor region and can get changed in liquid region, then can I see that I will have to mind this word, these things also, that in liquid region I will use which specific heat? Specific heat in the liquid region and specific heat in the vapor region. So we will have to take care of this fact also. Okay. So tell me, if somebody has given you another curve, like let us say this one, then the formula like which this one as H2 is equal to Cp dt, Cp T2 minus T saturation. These things you cannot use in this between these 2 points. Got the idea? Why? Because this is on another pressure curve and this is on another pressure curve. So you cannot apply this dH formula is Cp dt between these two curves. Why? Because you have two different what pressure curves, and this is applicable for whom? Constant pressure. So you can apply anywhere on the same constant pressure line, but you cannot apply on inter pressure lines. Okay. Now, and now when I desire to write down the entropy change, so entropy change will be again what? Entropy. We should know how to write enthalpy and entropy at various points. This would help you in so many subjects, like in um, refrigeration part, in power plant part, and sometimes in the internal combustion engines parts even. So entropy at various points. So you should be able to know that how to write down enthalpy and entropy at various points. Okay. So let me help you how to write down entropy at various points. So let me draw that curve again. So this is your, let us say, point 2, this is your point 1, this is your point 3. So here you have SF and here you have SG. See, a small case later means what? These are a specific property, that is per unit mass. So now can I write down S1 as is equal to S1 is equal to SF plus X into SFG. S1 is equal to SF plus X into SFG. Okay. And this SFG is equal to SG minus SF. Okay. And S is ds. This is nothing but ds, and ds is dq upon t, right? And dq is what? Change in the enthalpy. So can I write down this is hfg upon t? Okay. And this is also what? Latent heat upon T saturation. This is also T saturation only. Got the idea? Now I am writing down, this one is for wet region. Wet region. Now if I wish to write down the entropy at superheated region, superheated region, then then can I write down this equation? TdS is equal to dH minus VdP. This we have derived, right? And if I am writing on the constant pressure curves, then dP part is 0. So can I write down TdS is equal to dH? And can I write down ds is equal to dH upon T, and dH for constant pressure, can I write down for constant pressure any substance? I can write down this is mcp dt upon T. So can I write down ds is mcp log of T2 upon T1? Yes, I can write. And this is the idea that we will be utilizing. So here, if I am willing to write down for whom? Superheated region. So what will be the entropy change? Can I write down that ds is means what? That entropy change means S2 minus Sg. So can I write down S2 minus Sg is equal to, and in terms of a specific, so mass we need not to inculcate. Why? Because we have already taken in specific terms. So S2 minus Sg can I write down, and this is for vapor region. So can I write down this is Cpv into ln T2 upon T1? I can write. Yeah. Similarly, when you will be working with the subcooled region, so I am writing down here, and let me write in the next slide. So we have seen this concept now. So if we are working with subcooled region, then can I write down that SF minus S3 was in subcooled region is equal to Cp of liquid into log of what? T saturation. T2 was what? T saturation, and divided by T3. Got the idea? Why? Because log of ln T2 upon T1, right? So here your T2 is T saturation and T1 is the point which we are talking about. Okay. So this is how we used to write T2, T1 and other things. Means enthalpy, entropy and internal energy at various points. Okay. Okay. So this is where this is how we will write down. Like you will see the application of this. If you understood this carefully, then you can find that this is the basic thing which you should know before writing enthalpy change, entropy change, because these changes are very much counted where you are talking with the phase changes, and where we can see these things in the power plant applications, in the refrigerations, and where sometimes in the what IC engine parts. Yeah. So we'll stop it today, and then we will continue in the next class, and that will be probably the next class. Only few things are remaining, few problems we'll do, and things to understand are left. So we'll be probably finishing this on the upcoming class. Okay.